Alright, we'll take a closer look at some of these simulations you were supposed to have done in the lab today because some of you did not get the answers right. Some of you didn't answer anything at all. And this is important stuff that you're going to have to know for our next test. So this is the skate park one. And basically you had to build a track and you had to make the track work and all. The key here though is understanding kinetic and potential energy. Where it's highest, where it's lowest, how it's changing as the skater moves through the track. And really all we need to examine that more closely is this simple back and forth U-shaped track. I'm going to slow them down and we're going to stop them up here at its starting point. Where the skater starts, the skater is at the highest position. It's furthest off the ground, which means the skater has the most potential energy. We can see that here in the bar graph, and we can see it in the pie chart that's hovering right above him. At this point, the skater has the potential to move. That energy can't be converted to kinetic as the skater rolls down the hill. So let's let it happen. See, as the skater moved down the hill, lost some of his height, some of the potential energy was converted into kinetic energy. The potential bar went down, the kinetic bar goes up. You see it in the pie graph too. Blue is potential, the green is kinetic. We've lost some of our potential energy and we've replaced it with kinetic energy. Let them roll all the way down to the bottom. Again, watch the pie chart, watch the bar graphs. The further down the slope he goes, the more potential energy is lost, the more kinetic energy is gained. Losing potential energy because he's getting closer to the ground, the thing that gives the object, in this case the skater, potential energy. Gaining kinetic energy because he's moving faster and faster. Whenever something is moving towards the ground, it doesn't matter if it's a skater, dropping a ball, whatever the case might be. As it gets closer to the ground, it loses potential energy. As it speeds up, it's gaining kinetic energy. So roll up the other side and see what happens. As he rolled up the other side, the kinetic energy dropped. That loss in kinetic energy is because the skater is moving out of his resting position. It's being converted to potential. We notice the loss of kinetic energy because he's slowing down as he goes up. So again, that kinetic energy is dropping, that potential energy is rising. This is a conversion from kinetic to potential. It happens anytime something moves off the ground, be it the skater going up the ramp or lifting something up off the floor. Let me let it run. And again, you can see it changing back and forth. As it goes down, the kinetic builds. As it goes up, the kinetic disappears. As it goes down, the kinetic builds. As it goes up, the kinetic disappears. The faster he's going, the more kinetic energy he has. The slower he's going, the less kinetic energy he has. That velocity is one of the things that affect kinetic energy. When he's all the way at the top, he's got a lot of potential energy. Down at the bottom, he has the least. At the top, he has the most. This is gravitational potential energy. Being off the ground gives the object gravitational potential energy. The further off the ground he is, the more potential energy he has. Far off the ground, lots of potential. Closer to the ground, less potential. Now note, it stays this circle. The amount of blues and greens change, but the size of the circle does not. The total energy stays the same. Over on the bar graph, we see the same thing. The kinetic goes up while the potential goes down, meaning the total energy in the system remains constant. This is the law of conservation of energy. Let's go ahead and close that and move on to the pendulum. And it's the same story here, really. It's all we're looking at is this change from kinetic to potential. There's no energy in the system right now because the pendulum's hanging in its resting position. As we move it out of its resting position, we give it potential energy. Again, down here in the resting position, no energy. That's where it wants to be. Lifting it up gives it gravitational potential energy. When I hold it here, it's all potential. and it won't start converting it to kinetic until I let it go. When I let it go, it starts to fall, and as it falls, the kinetic goes up, but the potential drops. It's getting closer to its resting position, so it's losing potential, and it's moving faster, so it gains kinetic. As it swings up the other way, we see the opposite change. The kinetic drop, the potential go up. It's slowing down, so it's losing kinetic. It's moving further away from this resting position, so it's gaining potential. Whole process starts again. It falls and the potential drops. Kinetic rises. Speeding up gives it more kinetic. Being closer to the resting position gives it less potential. As it rolls back up again, same story we had on the other side. Slows down and the kinetic drops, and moves out of its resting position so the potential rises. Again, the total energy stays the same. It might change from potential to kinetic and back again, but the total energy in the system stays the same. This is conservation of energy.